This is the Math 2 lesson summary video for the lesson entitled My Irrational and Imaginary Friends. In this lesson, the purpose is to develop meaning behind irrational and complex numbers. Recall that if our quadratic function does not cross the x-axis, then we say that our solutions are imaginary. By the end of this lesson, we are able to write our solutions in what we call complex number form. This form is a plus or minus bi, where a and b are real numbers. We also discover in this lesson that I is equal to the square root of -1. In prior lessons from this unit, we realized that we can solve a quadratic function using the quadratic formula x equals -b divided by 2a plus or minus the square root of b squared minus 4ac divided by 2a. We discovered that when we have a negative under the square root, such as the discriminant, which is under the square root, is -121, we saw that when we graphed it, the parabola did not cross the x-axis. Therefore, in this lesson, we are going to learn how to write these in complex number form. We know that when the parabola does not cross the x-axis, there are no real solutions, and now we are going to discover how to write those solutions in imaginary numbers, as imaginary numbers. In 1, we are asked to verify that 4 times the quantity x minus 5 halves times the quantity x plus 3 halves equals 0, and that 4x squared minus 4x minus 15 is equal to 0. So if we use our prior knowledge and we distribute what's in parentheses, we're first going to work with distributing our parentheses together. So x times x, we know I'll bring down the 4 is x squared. That would be plus 3 halves x minus 5 halves x. And that would be then a minus 15 fourths. Now we need to distribute the 4, which we can also combine first what's in parentheses. So we would get in parentheses, and as well as we distribute the 4, a 4x squared minus 8 halves, which is minus 4x, plus 64ths, which indeed is -15 equals 0. So we are showing mathematically that they are equivalent, and then we are asked to solve. So we can do that using the quadratic formula, or we can use our graphing calculator and do our trace function calc. When we do that, we get x equals 5 halves and x equals -3 halves. So we're going to plot where those would be on the number line. So 5 halves is 2.5, so that would be approximately here, and -3 halves would be -1.5, so that would be about here. And we know that those are rational numbers, and we can plot them on the real number line. Okay, moving along to number 2, we are asked to do the same thing, but we do see that there are some complex numbers. Just erase what's here. So if we look, and I highlight here my complex number, we do see that we are going to have to distribute still in order to see if these are equivalent to this quadratic function. Remember that when you factor, you can set your factors equal to 0 to solve. So they're asking us to see if these are equivalent, and then we can easily solve if we look at these factors. So let's multiply them. That would be an x squared. We do have to multiply the -2 times the x, -2x. The negative root 2 times the x would be minus x root 2. Okay, so we're distributing the x. And then we're going to move along to the -2 times the x and the negative root 2, or the -2 times the -2, which would be a plus 4. To finish this off, we need to distribute our last two terms. So we would get a plus 2 root 2 plus x root 2 minus 2 root 2 minus 2. Because when you multiply a square root times the square root cancels and it's a minus. So there would be a minus 2 on the end. Now we need to combine like terms. So we'll highlight our like terms. I see a -2x here, a -2x here. So if we simplify that and we combine our like terms, bring down our x squared, we get x squared minus 4x We have a negative x root 2 and a plus x root 2, so those will cancel out. We have a plus 2 root 2 and a minus 2 root 2, so those will cancel out. And then we have, and I'll highlight these in a different color, we have a plus 4 and a minus 2. So the plus 4 minus 2 would give us a plus 2. And of course, that's equal to 0. So we can see that they are equivalent. Now, if we use what we did, the quadratic formula, or we can use our calculator to find the zeros of the function, we can see here on the left that two of our solutions should indeed be 3.41 approximately and 0.59 approximately. And those are irrational solutions. So we can plot them on the number line, but they're not rational, they're irrational. So let's get to our number line and plot those. 3.41 will be approximately here, and 0.59 will be approximately here, okay? So the whole purpose of 1 and 2 is for us to see that we do have rational solutions as well as irrational solutions, and we can see those when we use the quadratic formula. So the first big idea of this lesson is that the set of numbers that contains all of the rational numbers and all of the irrational numbers is what we call the set of real numbers. And you've been working with real numbers up until this point in your math courses. The location of all points on a number line can be represented by real numbers. Now we're going to move to, well, what about imaginary and complex numbers? Can we plot those actually on a number line? So part 2 of this lesson tells us, as Leonard Euler had discovered, that I is equal to the square root of -1. We are asked then in 6 to figure out if that's the case, if I is equal to the square root of -1, then how would we simplify I squared? Well, if we substitute the square root of -1 where we see the I and we square it, we know mathematically that the square does get rid of the square root. They cancel out, so I would be left with -1. Likewise, we also know that we can rewrite that as -1 times itself. That would also mathematically be the same thing as the quantity the square root of -1 squared. And when we multiply the square root of -1 times the square root of -1, we still get -1. So I squared would be equivalent to -1. We are then told that the square root of -2 we can rewrite as the square root of 2 times the square root of -1. So we can rewrite that as the square root of 2 times I, since I is equivalent to the square root of -1. And we are asked to simplify some other examples in number 7. So if we look at the square root of -16 and we follow the same pattern, we would rewrite that as the square root of +16 times the square root of -1. Because when we multiply those radicals together, we do get the square root of -1. The square root of 16 is a nice number, that is 4, and the square root of -1, we can replace that value with I. So we would simplify the square root of -16 into 4i. On the next one, we have a 2 on the outside, so we're going to bring that down, and we're going to rewrite this radical as the square root of 121 times the square root of -1. Bring the 2 down again, the square root of 121 is 11, and the square root of -1 is I. Therefore, we can rewrite this as 22i. We're going to use this in order to simplify when we are now solving quadratic functions where they do not cross the x-axis. So to summarize, the big idea number 2 of this lesson is to tell us that numbers like 3i and root 2i are what we call pure imaginary numbers in mathematics. Numbers like -2 minus I and -2 plus I that include a real term and an imaginary term are called complex numbers. We are now going to try to solve some of these quadratic functions that have imaginary solutions. We are asked to examine the roots of the parabola in 9 by discussing where the -b divided by 2a is in the graph. And in our function, we are working with x squared minus 6x plus 7. So they're asked where these show up in the graph. And if you recall in a prior lesson, we do know that the -b over 2a is the axis of symmetry. We can plug into our formula, -b over 2a, in this case a is 1, b is negative 6, and c is 7. So negative b would be negative times negative 6 divided by 2 times 1, 6 over 2. So my axis of symmetry should be 3. And we can see that the axis of symmetry does go through the max of the min, which is right here at the point or the line x equals 3. And then they're asking, where does the root b squared minus 4ac over 2a end up in our function? Well, we do know from our prior lesson that that should be the distance, the d value, from the axis of symmetry to my x-intercept. It's a matter of us finding what that is, so we can plug in the square root of b squared minus 4a times c divided by 2 times 1, and we'll get the square root of 36 minus 28 divided by 2. And 36 minus 28 is equal to root 8 over 2. And we can simplify that into root 4 times root 2 over 2. And root 4 is a nice perfect square. That's equal to 2 root 2 over 2. That cancels. So root 2 should be my d, plus or minus root 2 should be my d, or my distance, from the axis of symmetry to the x-intercepts. So therefore, we know that 3 plus root 2 and 3 minus root 2 should be our x-intercepts, or our roots, to this quadratic function. And we can see that those will be irrational solutions, but they are indeed real. We then are moving along to 12, and we're asked to find some complex roots. So how do we know that this has complex or imaginary solutions? We can see visually that the parabola does not touch the x-axis. Therefore, we know that its roots are going to be imaginary. We can easily find the equation of this parabola in vertex form. If you recall from our unit 4, the vertex in this case is the point -2, 3. And in our standard vertex form, it's a times the quantity x minus h squared plus k, where h and k is the vertex. So we're going to plug h and k in. We'll get x plus 2 squared plus 3. And recall also that we can find the a value. The a value will be from the vertex over 1 up 1 times a. So if 1 times a equals 1, then a must equal 1. So in this case, I can change that a. I know it's 1. The other option for us is to actually plug in another point, such as 0, 7, which looks like our y-intercept, and plug that point in for x and y to get the a value. But I indeed know that this will be my equation, and let me just write that x plus 2 squared, because we do not need to have the 1 in front there. So x plus 2 squared plus 3. Now let's write this in standard form. So let's distribute the x plus 2. And when I do that, I'm going to get x squared plus 4x plus 7. Because recall, you have to distribute what's in parentheses and then add the 3 on the end. So this is my standard form of this parabola. Now we're going to plug into the quadratic formula, and we'll do this together so that we can find what our complex solutions are. So x equals negative b divided by 2a, which is always our axis of symmetry, plus or minus the distance to the zeros, which will be always found by the square root of b squared minus 4ac all over 2a. And recall that's from our previous lesson. So let's find our a, in this case, is 1, our b is 4, and our c is 7. So negative 4 over 2 times 1 plus and minus the square root of 4 squared minus 4 times 1 times 7 all over 2 times 1. So x equals negative 4 divided by 2, we know will end up giving us negative 2. So we know our axis of symmetry should be at the line x equals negative 2, and I can see visually that that indeed is true. X equals negative 2. So now it's just a matter of us finding the imaginary solutions, because it does not cross the x-axis. So let's do that math. Under the square root, we're going to get 4 squared, 16, minus 28 divided by 2. So x equals negative 2 plus or minus square root of negative 12 over 2. Ta-da! So we can see that under the square root, our discriminant is negative. This indeed has imaginary complex solutions. So now recall that Euler was nice enough to give us I is equal to the square root of negative 1. So moving forward, it is expected that you can write this as an imaginary or complex solution. So I'm going to rewrite the square root of negative 12 into the square root of 12 times the square root of negative 1 and divided by 2. The square root of 12 we can break down into the square root of 4 times the square root of 3, and the square root of negative 1 is just I. That whole thing is divided by 2. So negative 2 plus or minus square root of 4 is 2. 2 root 3i over 2. And that's kind of nice because my 2's will cancel. And so I know my complex solutions will be 2 plus or minus square root of 3 times I, and I'm done. I just wrote my solutions in complex number form. So our last big idea of this lesson is that complex numbers are not actually real numbers. They do not lie on the real number line, such as in the previous example. We cannot plot negative 2 plus or minus the square root of 3 times I on a number line. And note that real numbers are a subset of complex numbers, since a real number results when the imaginary part a plus or bi is 0 and the a plus 0i. So the main goal of this lesson is you can now write an answer in complex number form. In summary, we can find our imaginary complex solutions by knowing that I is equal to the square root of negative 1. If our discriminant b squared minus 4ac is negative, we rewrite that as a positive radical multiplied by the square root of negative 1. We then change the square root of negative 1 to I. If you need more help on the Ready, Set, Go homework for this task, please check the Canvas Student Support site.